Okay, let's get started. But before we do, are there any questions about the homework due on Thursday that hadn't already been answered on CampusWire about either the first one or the second one? Yeah. Okay, well, make sure to do that because Thursday is the last official class session of the semester. So we'll talk about the answers then. So we can't have anyone taking an extra day or anything like that for this one. Okay. So this week we're going to talk about missing data and how you can deal with missing data problems using STAN. As usual, employee of Columbia seeking to develop grants, develop STAN. Actually, in the last week or so, we were promised an additional grant for developing STAN. So this is not just like ancient history stuff, actual ongoing conflict of interest due to using STAN outside of Columbia, creating the appearance of conflicts of interest and whatnot. So before we talk about like truly missing data, we want to talk about measurement error, which is sort of partially missing data. So you have observed data, but it is disconnected to a greater or lesser extent than the true data that ostensibly has the relationships that you're modeling. So in most, not necessarily all, but the vast majority of cases, when you say like, you know, the conditional mean of y is linearly related to x, you mean the person's true value of x, their true age, irrespective of what age they say they are on the survey, or their actual income, irrespective of what income they might tell you or what income they might tell the IRS. But moreover, there are some models like in economics that say, you know, things like a person's consumption now depends not on their income now, but on their so-called permanent income, which is sort of their expected income. And so, you know, their actual income may deviate from that, but the model, the theory of the model is sort of specified as this sort of true expected income sort of thing. Anyway, everyone, like literally everyone, agrees that variables that are typically used in the social sciences are measured from, differ from the true concepts they're intended to be operationalizations of by a considerable margin for a lot of the variables that we want to use in the social sciences. And there's really like, you know, all papers or whatever that talk about this say, well, the first thing we should try to do as social science researchers is measure the variables better. But there's a limit as to how well that could even, you know, it could be done better. But there's a limit to how well that could be done, particularly for social science variables that are commonly used. And so even if it were done better, it would still be done pretty bad. Moreover, all people who have thought about this from a frequentist perspective agree that measurement error is harmful for frequentist estimators to a greater or lesser degree. In one very special case, linear model, no link, Gaussian errors, and the only measurement error is not only completely random, but it's confined to the outcome variable, then in that case, ordinary least squares is still the best linear unbiased frequentist estimator. Best in the sense that it has the smallest variance across data sets in those point estimates. But the standard error of the residuals is just larger than it would be if y, the outcome variable, were measured perfectly. So in that one case, measurement error causes no bias across data sets, and it does not change the fact that ordinary least squares for fixed x is still the best linear unbiased frequentist estimator. But that's an extraordinarily special case. In only a slightly different case, still linear, no link, Gaussian model, etc. But now you have random measurement error on exactly one of the predictors. Then it is well known that the coefficient on that predictor, if you condition on your observed predictor that has the measurement error in it, the coefficient is going to be biased towards 0, that is to say attenuated, and the coefficients of all the other variables are going to be also biased but in indeterminate directions. And the magnitude of all this depends on how bad the measurement error is. In a more realistic situation, like you have other likelihood functions, you have measurement error on multiple predictors, etc. Frequentist estimators are biased across data sets, and not much can be said about the direction or really the magnitude of bias of particular coefficients without making additional strong assumptions, like the covariance between the measurement error on one variable and the measurement error on another variable or something like that. So overall story here is that measurement error is not good, and only in a few cases do we even know how it's not good. But that does not come anywhere close to exhausting all the cases in which frequentist measurement errors have been, or measurement error on variables that people have used with frequentist estimators. And this is, I think, sort of odd state of affairs, and one that someday might cause a fairly radical rethinking of previous results in social science that have been published, in addition to all the stuff that psychology is going through, because it's basically a convention that journal editors and journal reviewers and whatnot just let measurement error slide, in the sense that I don't know of any person who's ever had their paper rejected because the reviewer or the editor said, oh, I think those variables are measured with error. That is going to mess up your results in, for more or less unknown ways. So I don't believe, anything that you said. So I don't think this paper is going to be published. That doesn't happen, as far as I know of, in social sciences, because those same journals have been publishing for a long time empirical papers with variables that have been horribly measured, and those same reviewers are sending papers to those journals that they hope to be published. So it would be a bit arbitrary and unfair to all of a sudden say, you today, no more. That paper has too much measurement error, so we're not going to publish it. And so more or less there's this truce or convention among social science researchers that they're not going to complain too much about the measurement error in somebody else's study, because you don't want other people to complain too much about the measurement error in the variables in the studies that you're conducting. But that's just a convention. It's not something that has any actual methodological justification. And it's one of those things that is just sort of sitting out there on a fairly thin branch. And one of these days, the state of opinion might switch pretty strongly, and it becomes another reason why, all the results for going back many, many years that have been published in journals can't really be trusted. And so that might happen someday. And there's not that much you can do about measurement error from a frequentist perspective. The really only good option you have is to integrate the variables that have been measured with error out of the likelihood function the same way frequentists do random effects models. So considering that group-specific intercept, group-specific slope, etc., to make a contribution to the error term that causes those to be correlated, and then integrate those problematic things out of the likelihood, maximize it with respect to the other parameters, and then you get a different estimator. But that's impossible to do analytically unless everything is Gaussian. It's pretty poor numerically unless you use MCMC to evaluate integrals. And so that's another weird thing about 2019 is that these more complicated likelihoods that frequentists have been coming up with these days often require numerical integration in order to evaluate. And the only good way to do those integrals is with MCMC, which is associated with Bayesian techniques, but really it's just a way to do definite integrals. So you'll see, frequentists doing simulated likelihood and then maximizing that when it would be just as easy to just draw from the posterior distribution using MCMC. It also ignores the distinct possibility that the true values of the data might be of substantive interest. If you integrate them out of the likelihood, then you can't estimate what those true values were. But in contrast to all that, measurement error can be handled in a Bayesian analysis without introducing any new concepts at all. You can't just ignore it and expect to get awesome results. But in order to take into account, all you pretty much have to do is think of the true values that are being measured with error as additional unknowns, and get the posterior distribution of them along with everything else. So if we have Y star as being the true outcome, and we have a vector of parameters in phi that govern the process by which the observed value that we have data on gets measured, which is to say mismeasured relative to the true value Y star, then we can easily define a posterior distribution or posterior PDF for Y star, theta, which is the parameters of interest, and phi, which are these parameters that are not super interesting, but quantify how well or how poorly Y is measured. We condition on the actual observed values of Y, and we can get a posterior numerator of Bayes' rule that can be written as, prior on theta and phi. Oftentimes those would be independent of each other a priori, times the conditional PDF of the true data given the parameters theta, times the conditional PDF of the observed value given the true value. And then there's additional parameters phi that sort of capture the extent of the measurement error. So no new concepts, just using the multiplication rule 3 times instead of 2, or there's 3 terms in the multiplication rule instead of 2. But there's no new ideas at all here. And Stan is particularly good at drawing from posterior distributions that have a lot of dimensions. So you might say, oh, well, Y star has n elements to it. Now I have this huge posterior distribution if n is large. Well, Stan doesn't really care. It may take longer. but it doesn't make it like fundamentally orders of magnitude more difficult for no U-turn sampling to draw from this posterior distribution. And if you don't actually care about Y star, if you only care about theta, then just kind of ignore the draws on Y star and phi and focus on the posterior draws of theta. But, you know, conditional on the observed Y, you know, theta star and or theta and Y star and phi, they're not independent of each other. So by drawing from their posterior distribution jointly, you get a more honest, but also typically more precise posterior distribution on the things that you care about. If that's theta, then so be it. So that's sort of the basic idea of how we're going to attack measurement error with Stan. Is there any questions about that before we jump into the code? No? Okay. So let's switch it around a little bit and think about the measurement error as being on our predictor variable instead of on our outcome variable. It still has 0 new concepts, but let's show how we can do that, and let's show how we would do it with SBC so we could verify that Stan is going to work well in a situation like this. We pass in n, which is the number of observations, declare x underscore, which we're going to think of as like the true values of the predictor, x obs, which we're going to think as the measured values of the predictor, and also y, which we're going to draw from its prior predictive distribution. And then we have, okay, let's say we have a normal prior on the true x. It has a mu x and a sigma x underscore that we're going to draw from our priors on those, like normal, exponential. You could easily change these priors to be something else, but you know, some prior on the mean and the standard deviation of the true x across people. Then we're going to draw tau from an exponential distribution, which has a rate of 10, so an expectation of 0.1. Tau is, in this case, is going to represent the standard deviation of the measurement error in x. So when we get to okay, when we drop down here into the loop over observations, we're going to draw like a true x from normal mu x sigma x. Then we're going to draw x obs from normal with expectation true x and standard deviation tau. So this starts to look like meta-analysis. And that's kind of the point, because this is just a hierarchical model, and that's all meta-analysis is. So anyway, the relationship between y and x is governed by an intercept alpha and slope beta. So we draw those from the priors. And then, you know, y has error as well. So we get priors for all that. And then we draw from the prior predictive distribution of y, normal with expectation alpha plus beta times true x. And then with standard deviation sigma y. So the prior predictive distribution for y is generated from the true x, not from the observed x. So we're saying your response depends on your true income, your true age, not whatever number you tell the survey data collector. So that's all plausible. Okay. So pretty simple process that we're reflecting here for the data generating process. Then we declare true parameters, tau, mu x, sigma x, all those. Only difference is we have z, which I am thinking of as a standardized version of the true x. So in my model block, the first thing I do is create x, which is sigma x times z plus mu x, to be my vector of observations that I think my beliefs about the true x's. Then create eta, which is just alpha plus beta times the true x. to be my conditional expectation of y. Then priors on all these things, inclusive of z. So if z has a standard normal prior, then that implies x has a normal distribution. If I scale up a standard normal random variant and shift it over by mu x, then it has a general normal. Okay, that's fine. And then just densities for all these distributions corresponding to how I think the data were generated. Build up the numerator of Bayes' rule. And then, here's like the likelihood statement. And then, the rest of these are priors on the unknowns. And then that defines the numerator of Bayes' rule. And it's ready to go. So, I mean, you can look through the details of that, but what I really want to emphasize is that, like, those are just details. And the concepts we've been yammering on for, like, over 3 months now. And then the generated quantities block, when you're doing SBC, need to declare a vector called pars underscore and an integer array called ranks underscore, which are both of the size of the number of parameters you want to keep track of. In this ranks thing, you just tabulate whether the posterior draw was greater than the prior draw. And, when you look at the results at the end, there shouldn't be any systematic tendency for the posterior to be different from the prior if you're conditioning on data that was generated from the prior predicted distribution of the model you're fitting. So if you condition on prior predictions from the model, you just don't really systematically get anything different from what the model already assumed, which was the priors. And then you copy into the 6 elements of pars the draws from the transform data block. So it has those as well if you need to look at their distribution. We could calculate up the log likelihood function, but we'd have to do numerical integration to integrate out z, and we don't want to get into that today. But anyway, that would be sufficient, and then you could get the SBC function, run this a bunch of times, and verify, okay, Stan can do that well. So questions about that or about the code for the model? Yes. So I could have just called this X and given it a normal prior with standard deviation sigma X and expectation mu X. What you'll oftentimes find with Stan, if you do it that way, is that the posterior distribution is going to have a lot of weird dependence between Z and or between X and sigma X. And that's because, like, when you get a posterior draw of sigma X that's big, then all the Z's can differ a lot from, like, all the X's could differ a lot from mu X. And when sigma X, you get a posterior draw that's really small, then all of the X's has to be really concentrated around the mu X. And what that does to the posterior distribution is, in some places, like, the variance of everything is narrow, and in other places in the parameter space, the variance of things are bigger. It makes it hard for Stan to use a single step size in order to be getting around the posterior distribution efficiently. So really what it needs is like a small step size in one part of the parameter space and a big step size in the other part of the parameter space. And what it tends to do is land on like a medium size step size, in which case you get like a lot of divergent transitions because the medium size step size is too big in the small region. And it takes a long time because the medium size step size is too small in the region where we need big steps. And so what you can do is, without changing the posterior distribution for like alpha and beta and sigma x and mu x or any of those other things. Okay, declare z as your parameter, give it a standard normal prior. So now z under the prior is independent of sigma x and mu x and everything else for that matter. And then if you create x as a local variable inside the model block, well, Stan doesn't really care about that. It's just the intermediate variable. All it really cares about is what's in your parameters block and how do I evaluate the numerator of Bayes' rule. And so we can use the property of the normal distribution or indeed anything in the location scale family of distributions. We can take, something that has a standard normal prior, scale it up by sigma x, shift it over by mu x, and this implies x is going to have a general normal distribution. But the fact that I've encoded more or prior independence between z and sigma x means that there's a more consistent step size for Stan to be drawing from this posterior distribution on the z dimensions. And that can enable Stan to draw more efficiently from posterior distributions like this, or indeed, you'll see similar sorts of techniques in all multi-level models, or not all, but most of the multi-level models that people are doing in Stan. And so by doing it this way, we get more independence between z and the rest of the parameters in the posterior distribution, and that makes it easier to get a good effective sample size of everything. So you'll see anytime people are using distributions in the location scale family, normal, student t, things like that. You've seen me do it with the exponential, which is not location scale, but I can multiply an exponential with rate of 1 by any expectation, and now it's exponential with that expectation. Those sorts of techniques where you sort of declare in the parameters block a standardized version of the parameter, and then in the transform parameters or the model block, you unstandardize it by scaling it up, shifting it over. Those are the sorts of things that make it easier to get a good effective sample size with a small number of relatively small, a few thousand nominal draws from this posterior distribution. So another situation that comes up a lot is we have variables in the social sciences that are treated as if they're continuous, but they're actually rounded, maybe not to the nearest 1, but they could be rounded to the nearest like 1,000 or whatever. And so I don't know, like I wouldn't worry about cents being rounded to the nearest dollar, but if the rounding was like enough to matter, that could easily be handled in a Stan program, or this could be generalized fairly easily to any other data generating process that's interval censored. So like the lower bound and the upper bound of the true data value, but you don't know exactly what it is. You only know that it lies within one interval. So here we're going to think about data that have been rounded to the nearest integer. So we have n, we have k, which is the number of columns of x. In general, doing regressions, we want to declare x as a matrix instead of assuming there's just like 1 or 2 predictors or something like that. And then we have what we observe, which is the version of y rounded to the nearest integer. So we have a vector of that. We have alpha, we have beta, we have sigma for our regression. And we know there's some rounding error that if we're rounding to the nearest 1 digit has to be between -1/2 and +1/2. So the true value is equal to the rounded version of y plus a rounding error. So y is the integer, and then we know the true value, if they've done the rounding correctly, has to be within like half a unit of that. So we declare in our model block the true value of y or what we believe to be the true value of y, is the rounded version of y plus the rounding error. And then we have just a normal log likelihood for the true y given alpha plus x times beta, and the measurement error, or the standard deviation of the errors, sigma. We should add priors on alpha and beta and sigma, but that can be whatever you want. And implicitly, by not putting anything about the rounding error in our model block, that's equivalent to not including a term about the rounding error in the numerator of Bayes' rule. So that is equivalent to saying there's a constant probability a priori for each value of the rounding error between negative 0.5 and 0.5. And the logarithm of a constant is a constant, and Stan doesn't care about constants anyway. So if you don't include explicitly a prior on something that you declare in the parameters block, then implicitly you're saying a priori I have uniform beliefs over the space that you define for that thing in the parameters block. So this is saying a priori every value between negative 0.5 and 0.5 is equally likely under my prior, which is a entirely plausible thing to believe if you just have like cents that have been rounded to the nearest dollar. There's no particular reason why like 86 cents is more likely than 12 cents or something like that when it gets rounded away. So in the absence of adding a term for the prior, you're just sort of leaving that as a constant shape, which would not be a good idea for alpha, beta, or sigma. You should have substantive beliefs about those. But if it's really rounding error, you probably have no basis for thinking one value of the decimal places is more likely than the other. Questions about that? Yeah, again, so if you've been keeping up with the concepts and stuff pretty well, a lot of the stuff this week seems like a very small extension. And then it's just like, how do I write that in Stan code? Because these are the sorts of things that RStanArm and like VRMS for the most part can't currently do for you. But they're the sorts of things that are sort of well within your capacity to do yourself. Particularly if you start with like VRMS code, just like assume you have the true Ys or whatever, generate the VRMS code, and then change it to put in the rounding mechanism. No big deal. Questions? Okay, so moving from like data that's not quite right to data that's actually totally missing. The frequentist definition of probability is really not good for considering missing data in any substantive, useful way, because they define the probability of something A being true. The limit and the number of trials goes to infinity, the number of times that A happens as a proportion of the total number of random trials that you've done. But if there's some proportion of those random trials where A goes missing, you don't know what happened on that trial, then you can't evaluate the numerator. And so the probability is sort of undecidable if there's a non-zero proportion of those random trials where you don't know what the outcome of it is. And so the frequentist probability, when they were coming up with it, was not intended to be used in situations where like the person doing the experiment might not know the outcome of the experiment. But when you sort of extend it to observational data and other things that social science started to become after 1950 or so, it's totally possible that you might not be able to evaluate your frequentist estimator due to having missing this. So there's some things that you can do, but none of them are really that auspicious. You could assume the proportion of times that A occurs in the missing data is the same as in the observed data. Bayesians would say, well, that's your beliefs. Frequentists would say, no, it's an assumption. But that is a fairly arbitrary distinction. About the only thing that is actually a good idea is integrating the missing values out of the likelihood function and maximizing it with respect to everything else. But that's not going to be possible in very many circumstances. One thing that kind of sounds like a good idea and is actually a terrible idea is to maximize the likelihood function over the coefficients and everything and the true values of the observations that go missing. And that ignores the fact that the assumption for maximum likelihood estimator to be consistent or asymptotically normal or have any good properties at all is that the number of unknowns has to remain fixed as the number of observations goes to infinity. So if you consider the missing values to be unknown parameters, then the number of things to estimate is going to infinity at the same rate as the number of total observations is going to infinity. And maximum likelihood doesn't have any good properties in that situation, which is why when doing random effects models and you have this like separate intercept for each school, as the number of schools goes to infinity, the number of parameters to estimate would also go to infinity. So what frequentists have to do to estimate a random effects model is integrate those school-specific deviations from the common intercept out of the likelihood function and then maximize it with respect to the parameters. So if you can do that, then you just, maximum likelihood is valid or it's like admissible or whatever. But if you can't, if you try to treat the unknown, the true values for the missing as unknown parameters and maximize, the computer may run, but you'll get an estimator that is not consistent. It doesn't converge to any of the true values as the sample size goes down. For these reasons, the frequentist approach is really not useful for most of social science, because most of social science is going to have a lot of missingness on the variables that are being used in the model, and there's not very many good options here that don't require solving an integral analytically, which really the holdup for the Bayesian approach for many decades before we got good ways of doing MCMC was that like most integrals just can't be done. So yeah, you could do like numerical integral, simulated integral stuff, but then you're just sort of doing MCMC anyway. So you might as well take the Bayesian approach. So it's really, you could understand why it was done back in the 1920s or whatever, but Fisher defined probability so narrowly in an attempt to exclude the Bayesian approach from really sort of taking hold in 1925 or so, just deliberately defining probability so narrowly that definition of probability isn't that useful for so many circumstances that researchers wanted to apply quantitative methods later. You need a more general sense of probability as degree of belief. And once you do that, then it's like, okay, what do I believe the missing values were? What probability distribution would I ascribe to that? How would I update my beliefs about what the missing values were? And if you adopt a more general, more subjective Bayesian definition of probability, then you don't really have to like rethink anything in order to proceed. So how would we do something like that? So the true values of missing data are unknowns about which we have beliefs. We have priors on that. They're governed by probability distributions, and we can update our beliefs about those conditional on whatever data we observe. And so in that sense, nothing about this is fundamentally different from how we think about parameters, theta, intercepts, slopes, variances, etc. But we do need a way of keeping track of what values of the data are missing. So along with the reading from Van Buren, we'll define R as this sort of two-dimensional array with n rows and k columns. N is the number of observations. K is the number of variables. And this is just going to be a binary matrix. 1 if the kth variable on the ith observation is observed. 0 if the kth variable on the ith observation is missing. And then we can define a collection of random variables, xm and xo, and those they're not indicators, but basically xo is all the observed data, and xm is all the data that you intended to observe, but is actually missing when you get down to it. Then we have a vector of parameters theta that has our intercepts and our coefficients and other things that we would be substantively interested in. So if all the data were observed, then we would just be getting a posterior distribution of theta. But they're not, so we need some additional parameters phi, which are usually not that interesting, but govern how and which observations go missing and which get observed by the researcher. And so this is just sort of a very similar case to how we were thinking about measurement error in a Bayesian context. And then the posterior distribution of the substantive parameters theta, the less substantive parameters phi, and the true value of the missing data, conditional on the observed data and conditional on R. So that is what makes this a little bit different from a Bayesian analysis we've been talking about previously, implicitly assuming that all the data were observed. Then R would be like just all ones and not relevant. But we want a condition on R in addition to the true values of the data that we do observe. And then you can write the posterior kernel in a variety of ways depending on how you factor it. So we can write, posterior or prior on the parameters times conditional distribution of all the data put together and R given the parameters. Or we can write it like this. More common is to write it in the third line here. Prior on the parameters, conditional distribution of R given phi and the observed values of the data, and then times conditional value of the missing values given R, the observed values, and theta. So this third line here is what's known as the selection factorization. The second line here you don't see used as much. It's known as the pattern mixture factorization of the numerator of Bayes' rule. But what we're going to be talking about today is utilizing this third factorization of Bayes' rule here. And so we have 3 contributions to it. The prior contribution, R, which is basically a sequence of Bernoullis for what gets observed, what's missing, and then conditional distribution of the missing values given that it's missing, and the observed values and theta. So that's all a little bit abstract and mathematical. I think for most of the semester we've been focusing on how would we represent these ideas with code, particularly stand code. And so here is a function written in the Stan language for how we think the data would be generated under the so-called missing completely at random or MCAR assumption, which we'll get to toward the end of this function. So this is going to return an n by k matrix. We could call it s times if we wanted, but this is just going to be an n by k matrix. So we get k from the number of location parameters that we specify for our normal priors, and there's some other information that's going to need to go into these priors. So we start out by making a matrix for the outcomes, or in this case, all the data are outcomes really. We declare gamma, which is a scale parameter that goes into the construction of sigma. So this part here is maybe a little bit convoluted. It's actually how R prefers to build up a covariance matrix. So if we just read it from outside in, or inside out, we're going to draw from a Dirichlet. So that is going to be a simplex. What are the shape parameters for that Dirichlet? Well, I just copied my concentration parameter k times. So it's going to be, copy. So we get this simplex that is drawn from a Dirichlet. And then we're going to think of that simplex as the proportion of variance that each of the k variables that we're generating has out of the total. We're going to scale that up by k, which is the number of variables under consideration. And then the square root of that is going to be proportional to our prior standard deviations. But we scale that up by gamma so that we have this sort of overall parameter gamma governing how much or how little variability there is in all k variables. So we get this Dirichlet simplex to say in relative terms how much of the variance is in the first variable, how much is in the second, etc., all the way out from the k. And then we scale it up by k and we scale it up by gamma to give us absolute, in this case, standard deviations rather than variances. But we just take the square root. Then on the next line here, we build up the Cholesky factor. So this is being drawn from a RNG distribution called LKJ core Cholesky. So this is going to draw me a Cholesky factor of a correlation matrix. And by putting a k there, I'm saying, okay, I want this to be k by k. And by putting 1 for the second argument, I'm saying I want this correlation matrix whose Cholesky factor is being drawn here to be uniform over the space of correlation matrices that are positive definite. And so if this right here is a Cholesky factor of a correlation matrix that's randomly drawn, then I'm scaling that up by multiplying it by a diagonal matrix whose diagonal contains the sigmas that I just drew. So diag pre-multiply is a function. I'm not sure if we've talked about it yet in Stan, but it does just what it sounds. Like if you have a vector that you want to be part of a diagonal matrix and then multiply that on the left by some other matrix, well, you don't need to multiply by all those zeros. All you need to know is the diagonal in order to scale up the rows. So anyway, we use the diag pre-multiply function, use our vector of standard deviations to scale up the rows for a Cholesky factor of a correlation matrix in order to obtain a Cholesky factor of a covariance matrix. And we want to use that Cholesky factor for the covariance matrix to draw the true values of the data from a multivariate normal distribution. So this would also apply if you thought the data were generated according to some other distribution. But we're just using the multivariate normal here because it's like the simplest distribution we can use for k continuous variable. So all that is just like, and there's also a mu here for the expectations of the variables. This is all like how to draw the data, the true values of the data from a prior predicted distribution that is multivariate normal. But there's also this phi that I draw from a uniform prior between 0 and, let's say, 0.1. And this phi is going to govern whether my observations are actually observed or they go missing. So first I fill in mu with draws from like normal priors with a given location and scale that are passed in as exogenous arguments to my function. And then I drop into my loop over the observations. So I draw the true data values from a multivariate normal distribution, parameterized in terms of a mean vector and a Cholesky factor for the covariance matrix. So that's sort of the true data that I've gotten preliminarily. But then I loop over my k variables and draw from a Bernoulli distribution with probability phi. And if that Bernoulli comes up true, then I replace the kth observation or the kth value on the nth observation with NA, which is given by the function not a number in stand. So when those Bernoullis come up true, the value for that variable is missing. It's hidden from the researcher. But the fact that the probability of getting a missing value is just depends on phi, doesn't depend on anything else, not the data or anything like that. Just like one parameter that's independent of everything else makes this data generating process consistent with the missing completely at random assumption or MCAR. It's just like luck, really, as to what observations are actually observed and what observations go missing. It's not a function of any of the data, just as a function of a parameter. And so that is really the important part of this slide from here down to there. Yeah, you can assume the true data generating process is whatever you want. But in order for that data generating process to be missing completely at random, the probability of missing this can only depend on a parameter like phi. It can't be a function of the true data. And that's what we see reflected here. This is the data generating process under the assumption the missingness is completely at random. Questions about that? Okay, so if that is the data generating process, we can use it to think about practices that are very prevalent still and historically even more prevalent in the social sciences and probably a lot of other fields that are just horrible. So we can expose our function to R. We can draw, 100 observations on 5 variables from the process that we just defined in our STAN program, and we see that of our like 5 variables, there's like 5 observations that were missing on the first one, 7 on the second, less on the other ones, etc. And so by far the most common thing that you will see done in the social sciences is just if we were going to like do a regression or something like that involving, some subset of these variables or whatever, to just omit any row that has a missing value on any of the variables. This is what's known as listwise deletion or deletion by rows. And that would leave us 76 observations that had no missingness. Okay, well, from a Bayesian perspective, that should automatically seem suspicious because you're not conditioning on all the information you have. So let's say like 1 out of the 5 variables was missing on the first observation. Well, you're throwing out the whole row and not conditioning on 4 of the values that you actually observed for observation 1, just because it was missing on 1 of those variables. So you're certainly not taking advantage of all the data, not conditioning on all the information in the data. And that is something that Bayesians are reluctant to do. But under the missing completely at random assumption, if I just use these 76 observations in my regression or whatever, the coefficients and other estimates and whatnot would be unbiased, or the estimator is unbiased. But it is going to have more variability in the sampling distribution of the point estimates across data sets due to the missingness compared to this hypothetical situation in which there were no missingness. So under a missing completely at random data generating process, just using the observations that are fully observed on all the variables doesn't create any bias, but it doesn't take advantage of all of the information that you have. And moreover, people are doing things like this all the time, even if there's no basis at all for the missing completely at random assumption. Okay, so we could use X in a regression or whatever. It wouldn't hurt too much in this case. However, another thing that you'll see people do all the time is known as mean imputation. So just like make a copy of X and then loop over the columns, see which observations are missing, and then if they are missing, replace them with the mean value of all the observed variables, all the observed observations on that variable. And you might say, well, that enables us to use all 100 rows rather than just 76 rows. So that seems like it would be better. But again, from a Bayesian perspective, this seems ridiculous, and it is, because you're putting in the mean of each variable wherever it was missing, and then using that X in a regression or something like that. Are you as sure that the missing values are equal to the means as you are that the observed values are correct? You shouldn't be. There's no way you can be certain those missing values are any particular number. If you are approaching this from a responsible Bayesian perspective, you should have a probability distribution over all those missing values rather than a single number that you obtain from using the means of the observed values. Moreover, why would you only condition on the for making these mean values for your imputations? Why are you only using the other values in the kth column? Why aren't you sort of conditioning on all the other columns when you get there? So certainly by using mean values and not propagating your uncertainty about the missing values, this seems suspect, and it will lead you to get standard errors and whatever from your frequentist procedure that are too small. If the data generating process is actually missing completely at random, this also doesn't create any bias. But if the data generating process is anything other than missing completely, then this is biased as well, or it will result in biased estimators if you use these data. So these are two things that you'll see used all the time for dealing with missingness, both in like social science. You'll see this in supervised learning a lot, etc. And there's no real justification for that. There's nothing you can say, okay, if I think this is how the data were generated, and this is the process by which some observations go missing and others not, that would imply I should do either of those things, listwise deletion or mean imputation. But you'll see them done, and that's because today, but even more so a few or a lot years ago, the mindset of researchers was just like, can I get numbers? No real conviction, like, are those numbers like correct or unbiased or consistent or asymptotically normal, or any of these things that frequentists talk about when they derive their estimator. It's just, can I not get an error message and get numbers, estimates out? Because if I can get numbers, people felt confident that they would be able to tweak things in order to get the numbers that they want, with just like p-hacking, or, you know, exclude, you know, some observations and not others. As long as you can get numbers, eventually you'll get the numbers that have the right sign and are like hopefully statistically significant or whatever. Stop, publish, etc. But that is not a justification at all. It's just like, what dance can I do to not get an error message? Oh, well, just drop a bunch of observations and then go. Or like stick in some numbers. You're going to stick in a number, why not the mean? Okay. Now there's no missing this anymore. All gone. I get numbers. And if you have enough experience with doing quantitative analysis, you know that there's a lot of things that you can do to shift those numbers around, as long as you're not getting error messages. And that's really what prevailed for a long time, and even still today. Vicky, you had a question about that? So the magnitude of the problem is going to depend in part on how much missingness there is. In this case, we just have like 5–6%. But it's not just about the number of observations, but how much information is lost in these sorts of things. And so, as we'll see when we get into the Bayesian thing, you can have a lot of observations that have missingness. But if the true values of those things are predictable with a relatively small amount of error, then they're not so missing. So there's missing observations, which is sort of a yes/no thing, but that's a little bit of a red herring. It's how much information is lost. And so if whatever is missing can be predicted with a large amount of accuracy, then there's not so much information being leaked out. And that sort of depends on all the other variables. And so just counting up the number of observations doesn't really give you that complete picture. But it's certainly the case that if you had like 1 million observations and only 5 or whatever were missing, unless those were like super big outliers, whatever those true values are not going to have that much an effect on the point estimates, but you don't know that they're not super big outliers. Anyway, a different assumption about the missingness is known as missing at random, or MAR. So these are terrible acronyms, but one of the things that people get confused about is they think MCAR, MCAR, means missing conditionally at random, but that's not what it means. It means missing completely at random. The C stands for completely rather than conditionally. So there's no such concept as missing conditionally at random, but if there were, it would mean what missing at random means. And basically what missing at random means is, okay, we have like some variables that are fully observed, other variables that have some missingness. The probability of missing on any particular observation only depends on the variables that are observed, not the true values of the variables that are subject to missingness. And so here at the top of this, for generating the data, it's pretty much what we had before, other than I've introduced k-miss and k-obs. So let's say I have k total variables, of which k-obs are fully observed, and the rest have some degree of missingness. So as before, I'm going to generate all k variables, but what's different is I'm going to have one alpha, an intercept, for each of the variables that is subject to missingness, and I'm going to have a k-obs by k-miss matrix of coefficients governing this missingness process. The rest of this is, pretty much the same. It's just now I need priors on the alphas and the betas that I'm going to draw, those intercepts and slopes from. When I actually get down to n, the loop over n, the number of observations, okay, I'm going to again draw that from a multivariate normal distribution, the true values, with mean mu and Cholesky factor for that L, which was generated the same way that I did before. But the first k-obs of those are guaranteed to be fully observed. It's just the last k-miss values might have missingness. So I'm going to take eta, which is the first k-obs of the true values, and multiply it by beta. I meant to shift it also over by alpha, but I forgot. But anyway, I have this linear predictor for whether any of the last k-miss variables in my data generating process go missing. And so rather than what I had before, which was just like Bernoulli, all it does is depend on phi, it's some parameter, it's not a function of the data or anything like that. Now I have pretty much a loaded model where eta is the log odds that the observation on that variable goes missing. So if I draw that from a Bernoulli distribution with a logistic link function, if that comes up true, then I make the kth value missing. And so here we have a missingness mechanism, but the missingness probability depends on the data. But it only depends on variables in the data that are fully observed. So this is a little bit less general than missing at random could be, but the basic idea of it, okay, the missingness depends on the values of the data, but only fully observed values. The missingness, the probability of being missing, does not depend on the true values of the variables that go missing. So it's not the case that like people who have a lot of income are less likely to tell you what their income is, which is like definitely a thing. That would be inconsistent with missing at random assumption. But essentially missing at random is saying, okay, the probability of missing is not just like some constant. It differs from one observation to the next, but it only differs as a function of fully observed values. So if our data generating process is missing at random rather than missing completely at random, then list-wise deletion, mean imputation, all these things that you see social scientists doing, not only are not taking advantage of all the information in the data, they also yield frequentist estimators that are biased. But even missing at random is a strong assumption to make. It's not as strong as missing completely at random. But it's still a pretty strong assumption to say, okay, like I have missing this on the income variable, but which ones go missing and which ones don't are just a function of age. And age I have fully observed for everybody. So that would be the sort of assumption that you would be making if you assume that the income variable, the missingness on it, is missing at random. So it could depend as a function of people's age, but it doesn't depend on the true values of the income that go missing. But that is a pretty inappropriate assumption for most things in social sciences. We're pretty confident that when there's missing values on income, it tends to be from people who have a lot of income and they don't want to tell you or the IRS, etc., exactly what that income is, or from people who have very little income and probably not like a regular paycheck. And so they're not even really entirely sure what their own income is. And so they just say, I don't know. Anyway, in both of those situations, the probability of being missing depends on the actual value of income. And that's inconsistent with the missing at random assumption. So the general case, where the probability of being missing can depend on any of the true data values, is what's known as missing not at random, or MCAR, which is not to be confused with not missing at random, or NMAR, which is the same thing as MCAR. But both of those are a much weaker assumption than missing at random or missing completely at random. So the data generating process for missing not at random, similar, except the probability of being missing under my logits or observed can depend on all the true values, not just the subset of variables that I said would be fully observed. And if that's the case, then the data generating process is not missing at random or missing not at random. And in that case, when you do a model like this in STAN, if you're assuming the data generating process is missing not at random, then you need to include a part of your STAN model modeling the missingness mechanism. Like that's part of the generative model. Needs to explain why some observations go missing and others don't, at least probabilistically. If the data generating process were missing completely at random or missing at random, you don't have to model the missingness mechanism. Now, if it's missing at random, you do need to do some multiple imputation stuff for the missing values, and we'll talk about that more on Thursday. So you can't just do like listwise deletion or some single shot imputation or some other thing that social scientists like to do. That's still bad. But if it's missing at random, you don't necessarily have to model, although you could if you wanted to, the process by which some observations go missing, some don't. So you don't need a bunch of logit models on the columns of R. But in the more general and frankly more realistic case, where the missingness is not at random, it could depend on the true values of the data points that went missing. So people who are richer being less likely to tell you what their income is, etc. Then your STAN program, or whatever you're doing it in, but presumably STAN, needs to have a part of the model where you model the missingness observation mechanism. Why is it, in probabilistic terms, that some observations are observed by the researchers and others not? That has to be part of your generative model in order for you to get a coherent posterior distribution of the parameters you care about, the alphas and the betas and all the slopes and intercepts and whatever you want to do to make predictions and all that. So in order to get a good posterior distribution for the stuff that you care about, you also have to be modeling R. And that is what we want to encourage, but that is not what happens very much, particularly among people who want to be using frequentist estimators. So we'll talk on Thursday about what they do, different types of multiple imputation and stuff like that, which is better than mean imputation. But still, it's making pretty strong assumptions that are necessary to justify it. But if you do things just under the more general assumption of missing not at random, it's not really all that different. You just need to combine the model that you wanted to estimate with modeling the columns of R with like logits and stuff like that. So we'll see how that's done on Thursday. We'll talk about the homework and get through as much of the remaining stuff as we can. I forgot to copy the readings that come from the Gelman and Hill book for Thursday, so I will put those in a box outside the QMSS office like tomorrow, so you can go by and pick up a copy of that chapter to read about. Okay, so that's it for today.